Hey everyone, how's it going? My name's Austin Eubanks and welcome to the video for the first lab for Psych 5173 SEM for the Spring 22 semester. Start out with a few notes just to briefly discuss before we get started on the actual script. I'll be making some assumptions about everyone's level of R usage along the way, and in the interest of time, I'm going to try not to get too far into the details on a number of things. But at any point, if anyone has any questions, feel free to shoot me an email and let me know and we can work things out. I want to let everyone know that everything that we're going to be going over is just a way of doing things, and that there's not just the way of doing it. In fact, a lot of the ways that we'll be talking about things specifically in today's video aren't necessarily how I would go about something in a real world analysis. There are certain things that we'll be doing for sort of educational purposes, that there are extra steps that you may not necessarily take when you're working in a real world analysis. For instance, I'm going to do my best to stick with just tidyverse, baseR, and lavaan as our primary thing. So as far as the libraries, you will need to have tidyverse installed and lavaan. Also, I use PSYC for my go-to for just when I'm looking at general descriptives and whenever I'm looking for reliabilities. So when I'm trying to get alphas on scales and measures and things. So certainly we'll need those three packages installed for today. But across the semester, I'm going to do my best not to have just be throwing a bunch of different libraries with, just single functions here and there, because I don't want everyone to feel overwhelmed like they have to remember, 15 different libraries when mostly we're just working from lavaan and tidyverse. Tidyverse is essential for pretty much everything that we're going to be doing, and lavaan is the actual SEM library that we'll be working with. But that said, there are certain things that I just wanted to point out just in the beginning here. One being that there's a video that I've put up, tidyurl.com/tidyverse. That's a link to one of my videos. That's like an introduction to tidyverse for those of you who may not be as familiar with it. And in the tidyverse, Tibble is essentially synonymous with data frames. There are technically some differences between them, and tidyverse by default creates tibbles, and so we may call things a data frame, but if you look at the underlying structure, you'll actually see that technically it's a tibble. It doesn't really matter. Anytime you hear the word data frame, you can think tibble. If you hear tibble, you can think data frame. So if you hear me using those terms interchangeably, I don't want anyone getting confused about what that's talking about. There are a few keyboard shortcuts that I wanted to point out. One is called the section labels, which is Command-Shift-R or Control-Shift-R, depending on whether you're on Mac or Windows. And what that does is if I hit Command-Shift-R, it'll pop up asking me what I want my section label to be. And I can type in whatever I want that to be, and it puts in these headers like you'll see throughout these scripts. But the nice thing about it is that it automatically adjusts the length of the bar. So if you have a really long title that the words come out to here, it'll only insert this many dashes thereafter. But that also gives you a collapsible spanner, and so that can be really useful in a number of ways. Also, reflowing comments. So what that means is that if I am writing some big long comment that runs well off to the side, I can just keep typing and typing and typing and typing and typing. And instead of having this long comment that goes way off the side, I can reflow this comment with Command-Shift/ or Control-Shift/. And when I do that on this line, essentially what it will do is wrap that around and break it down into multiple lines and kind of keep everything nice, because in general, you don't want lines that run way off the screen. You want to be able to keep everything kind of tucked over along that left side so that you're just scrolling straight up and down and not having to scroll left and right. For inserting pipes, the default keyboard command is Command Shift M or Control Shift M. You can also change any of these keyboard shortcuts, and you can also find these keyboard shortcuts under the Tools button up on your menu bar up top, and look at your keyboard shortcuts help. Or if you want to change keyboard shortcuts, you can go to modify the keyboard shortcuts. But those are like the main three keyboard shortcuts that are really useful to know. The section labels helps you keep things really nice and organized. Plus, it allows you to have this outline view. So each one of these headers is one of those section labels, and that allows you to navigate scripts a lot easier and keep things nice and organized. For projects and working directories, I'm not really going to get into it too much. I may make a separate video to try to better explain what our projects are and how they work and why they're useful to you, for those of you who aren't familiar with them. There's, over the years, I've seen a lot of confusion about how our projects work and how they're used. But if you use the command get WD, that's the command for get working directory, and it'll tell you what your working directory is. So by default, right now, because I'm in an R project, my working directory is in my school teaching Psych 5173, Spring 22, Lab 1. In other words, this folder right here, this is my working directory because I am working out of this Lab 1 project. So what that means for you is, for instance, here where I read in the CSV and I have no file path, I just have lab1video.csv. That's because my working directory is by default where R looks for files if I'm trying to like pull something in, or if I'm writing something out when I write a CSV, or if I save and export a plot, it will by default put it in the working directory into this lab1 folder. So one of the assumptions that I'll be making is that everyone will be able to figure out how to deal with the file paths depending on where it is. So for instance, if you have it a folder in, my documents and stats, and you do get working directory and it just says like your user folder, then you may have to change that and put in a further file path to be able to link to wherever that file is. Or worst case scenario, if all else fails and you can't figure out where it is, you can always just try clicking on it, clicking import data set, and you can see where the URL or where the file path to that specific CSV is, and you can copy and paste that into your script where those file paths are. So again, feel free to send me an email if you want to understand more about our projects and how they work and why they're awesome. But for now, I'm going to try to not spend too much time on this video, trying to keep it as short as possible at least. One comment here, be careful about leaving things in your script whenever you're writing stuff. For instance, in your homeworks, we will be having you just submit the R script itself as your homework, so we can see the thing, and then we can see your code, and then you'll comment in answers to specific questions, etc. So if you are exporting plots or exporting CSV files, exporting tables, so writing data to some folder outside of R, and you just submit a script that leaves those things in your script and I run it, then it writes your tables onto my computer, and it could even overwrite files on my computer. So it's just good practice whenever you're writing and exporting things to make sure that you throw in that pound sign in front of it to block and comment out, and you'll see what that means when we get down to exporting things. So in short, I'll reiterate this when we get down to that, but just make sure you're mindful of your scripts, that they aren't writing things onto someone else's computer if you send that file to somebody else. Keep your scripts kind of contained within R itself. So that said, we'll get started with this first lab here. And so for the libraries, we're going to need tidyverse. And so when you open this up, one thing to pay attention to is the versions of things. If ever any of these scripts don't work, one of the first things to do is make sure that your packages are up to date, or at least as up to date as my packages are. So I'm on Tidyverse version 1.3.0, and for instance, my dplyr is 1.0.8. That may be important later on if you have a pre-existing version of Tidyverse. I know that in some cases you may be on a version that's pre this one, so it may be 0 point something, and there is at least one big change between the 0 versions of dplyr and 1.0.0 and beyond, with the addition of a function called across, which we'll see later on. So if things aren't running, that's one thing to always be mindful of, is when you load your libraries, what versions of those libraries do you have compared to what versions of the libraries I have in these videos, because that may explain why certain things do or don't run along the way. So we'll start by the first problem. We just want to read in our data, check our structure, and look at the descriptive. So we'll read it in with read_CSV, and then to check the structure, we use the glimpse function. Now, again, this is one of those assumptions that I'm making about understanding how pipes work, and so I'm just piping in this data frame that I've created into the glimpse function. And if that doesn't make sense, then I'd strongly recommend you check out this video at tidyurl.com/tidyverse. I think it's about half hour long, but it explains what the Tidyverse is, how it all works, and it explains in depth, for instance, how pipes work. And so if we pipe our data frame, our tibble, into Glimpse, we can look to see what it is. We have 2,386 rows with 5 columns being sex_F, birth region _US, DEP1, SE1, and SRA. Now, the way that I have these variables annotated, the sex_F, that's saying sex female. And anytime I have I give you a data set that has a binary 0-1 coded variable, whatever is 1, or rather 0 and 1 is false and true respectively in R. So if you have something that's coded as true and false, true will be 1, false will be 0. So if sex_F, that's saying sex is female. In other words, for every row, for every participant that it's sex_F equals 1, that means that they are female. 0 means they are not female. Birth region US means for everyone that has a 1, that means that their birth region was in the US. If it's 0, that means false, it was not in the US. This is just to make things easier for us here in the beginning. Really, these were character variables that were labeled as male and female. I've converted them to 0s and 1s for the sake of ease, in terms of not being able to put character stuff into matrices, or at least not being able to do the math that we're wanting to do later. And so in your real world analyses, you may have to be mindful of that sort of thing, where if you have, say, a gender variable, you might need to convert it to a numerically coded 0 and 1 variable for certain functions to work, etc. But for the sake of everyone's ease, we will be working on data sets that have already been reduced to a minimal form, and where we don't really have to worry about converting things, at least for now. So we have those. DEP1 are depression scores at a time 1. This is pulled from a bigger data set, but again, in this case, I've reduced it down just to these 5 variables of interest, so that we don't have to worry about if we want the correlation matrix of these 5 variables, that we have to start from a data set with 50 variables and reduce it down to just those 5 variables, and everything that we do just has only the variables of interest. And again, that's just for y'all's ease. So that DEP1 was a time 1 depression score, SE1 was a self-esteem score, and SRA was if I'm recalling correctly, a reading assessment score, essentially. Uh, what these variables are in this particular case doesn't particularly matter. We're just more so worried about how we can manipulate a few different things. So when you read these in, when we say like check its structure, which should be spelled the correct way, what we're talking about is checking, the number of variables, which is the number of columns, the number of observations, which is your number of rows, and then checking each variable. For instance, if we read this in, this DBL, that's saying double, which is synonymous with numeric, and it may be the fact that like we see that these are ones and zeros, but they're actually recognized as characters rather than actual numbers. And so this would say that this would let you know that it was a character or a factor or Boolean, those sorts of things. So you check what type of data each row is. And if, for instance, this was a character and then you tried to do math with it, it would tell you that you can't do that because you can't do math with what's essentially letters, even though those letters are, the letters 0 and 1, if that, makes sense. So checking your structure means looking at that underlying the size of your data frame, as well as for your variables, how are those variables encoded in the data set. In this case, again, I made sure that all of the data is strictly numeric so that we don't have any problems with any sort of math operations that we try to do with any of these variables. To check your descriptives, like I said, PSYC describe is my go-to function just for like quick glances at descriptives, because it gives basically all the descriptives that you'll want in terms of your in, your mean, standard deviation, median. One thing that you'll want to check always is those min and max values. In this case, we see that for sex and birth region, both min and max have 0 and 1, so that we know that that's just a dichotomous variable of some sort. With the others, with DEP1 and SE1, we see that the min and max is 1 and 4. And then with SRA, it's some score of 0 to 99. Now, when you're looking at these things, if we had age in here, for instance, and we had a min of 8, but that might be a problem, because if unless we're doing research with children, then that should be an error. If your consent form says that all participants must be at least 18 years old, that may be something that you need to look at. Similarly, if your max age is 1,956, chances are you had a participant who misunderstood and put in their birth year as 1956 rather than their age in years. And so those are the sorts of things that you want to look at when you're checking out your descriptives. We've also got our skew, kurtosis, standard error, etc. And the skew will come in to play a little bit later when we're looking at the distributions, but we'll talk about that when we get there. So for checking the missingness of your variables, you can use the map family of functions, which take some function that you put into it and they apply it across a data frame. It returns lists by default if you just use map. So if you use map DFC, it will instead return the output as a data frame that's bound by columns. There's also map DFR that will bind it by rows, etc. But so all you really need to know is that if we take our data frame and we run just this portion, just the selected portion where we pipe our data frame into map DFC and we put in the function is.na, what that's going to do is for each column, it's going to apply the function isNA, where it will return false if it's not a missing value, or true where it is a missing value. So on this value, for instance, on the second row, this participant is missing their SRA score. And so now we essentially have a data frame that has 2,386 rows of just trues and falses. So if we now take this data frame and pipe that into a function called means, which gets the means of the columns, remember I said earlier that in R, Boolean logic is represented with false equaling 0 and true equaling 1. And so, for instance, if we take our call sums, we can see that there are 0 trues in the sex, 0 trues in birth region. There are 23 missing values in depth, 24 in SE, and 248 in SRA. But if instead we pipe that into call means, we essentially get percentages of how much is missing. So we're missing a little under 1% of the depth variables. We're missing 1% of SE1 scores, and we're missing 10% of SRA scores, which, if you recall from lecture, missing 10% of a variable is potentially problematic, and you'd probably want to do something about that. For the purposes of the homework in the video, for now, we're not going to talk about what we actually do with those missing data, but rather just recognizing at what point does missingness become something that actually needs further consideration. For now, we're just going to note that, like, okay, well, 10.4% basically of SRA scores are missing, and that's as far as we're going to go for now. Dealing with missing data is its own very multifaceted problem that depends on a number of things as far as how you deal with missing data. So for now, we're just wanting to figure out how do we find out how much data is missing, and this is one way that you can do it. Again, all we're doing is we are taking our data frame, we are asking on each column, true or false, is this an NA value, is it missing? And then when we take the means of those columns, because false equals zeros and trues equal ones, we're able to break that down into a percentage. So the next thing that we're going to look at is looking at our distribution to take a look at the distribution of the variables, but also as a way of looking at our outliers. So we take our data frame and we're going to pipe it into our function called pivot longer, where we want to take our data frame from wide format into long format. And we just tell it for our calls, we tell it we want to pivot everything. And what that will do then, if we just run those two lines, is it just makes one big long one long data frame with two columns, name and value, that's almost 12,000 rows long. So now we take this data frame and we're going to pipe that into our ggplot. But the thing is that at the end of the line, we're going to facet this by this name column. So basically what this will do is we tell it in our aesthetics that we have an X, we want it to be this value column. And then whatever we plot, we want to break those plots into separate plots for each of these different columns. And so what happens when you put all of this together is that, for instance, if we use a geom histogram, it will produce histograms of each of the variables, and again, it will facet it by that name. One thing that I want to point out is that there are different ways of looking at your densities and outliers here. So if instead of doing histograms, if we use geom density, we'll get density plots of each of these variables. Or instead of, if we don't want density plots, maybe we want box plots, and we could use geom box plot instead. And each of these have their own values. I pretty much hate box plots for most anything, except for it can be convenient as far as like identifying really obvious outliers. In this case, for instance, our DEP1 and SE1, the values are only it's a 1 to 4 scale. But let's say that this wasn't just 1 to 4, and that you had if we go back to age, for instance, and have that example where we have an age that somebody put in 1956 because they put in their birth year instead of their age in years. It's really obvious to have that you have an outlier when you look at a box plot, because all this would be squished in real tight and there'd be one dot way down the line. But say, for instance, you were back to looking at a density plot or something, you'd have what looks like something, but then there'd only be one value way down the line, and so it would be it's hard to tell. Well, are there other outliers along the way, or are all the ages between 18 and 50, and then there's just this one value that's way up the line, or are there multiple values that are way up the line? That's a lot harder to see in like a density plot, because it would just look like a really long flat tail because of that one outlying value. Whereas with a box plot, you would see the box plot, and then way out to the side, there's just this one dot, and so you can go, oh, okay, that's a pretty clear outlier. So it's nice to look at things different ways. Some people prefer histograms, some people prefer density plots, and so really it's up to you. And here I just want to note that where I say scales equals free in our facet wrap, you can specify that's letting R know whether or not your X and Y scales are allowed to vary across your different facets. So if we don't have scales equals free here, what's going to happen is R is going to force everything to have the same scale. So even here on SECF, where our only values are 0 and 1, because SRA goes up to 100, it forces all of the x-axes to go up to 100. And so depending on what your data is, sometimes you want to let your x-axis vary, but you want to keep your y constant across so that you can have a consistent y-axis to look across all your different facets. So you would put in just free underscore x, or you want to allow your y to vary but not your x, so you would put free underscore y. So if you just put the word free, that means both x and y are free to vary. And again, this is the kind of thing where I'm trying to be short in the interest of not over explaining for those who are able to follow. If you're not familiar with ggplot, again, feel free to get in touch with me. There's also additional videos on the channel that are kind of intros to ggplot, where it explains a lot of these things in particular if you're less familiar with those. So for the next thing, we want to look at transforming variables. So depending on whether your skew is positive or negative, and just as a reminder, if the tail of that distribution is going up, pointing towards the positive side, that means that's a positively skewed variable. So in this case, DEP1, you can see that it's positively skewed. SE1, that tail goes down towards the left, which means it's a negatively skewed variable. And so depending on the amount of skew that you have, there's a few different kind of heuristics that you could use for what transformation might approximate normality as best as possible. In this case, with a moderate skew, you might start with a square root if it's a positively skewed variable. If it's negatively skewed, it's basically the same, but you have to reflect it, which just kind of means reverse scoring it. And so whenever we reverse score something, if you have a scale item and you need to reverse score that item, you just take whatever the max score is for that item and add 1 and subtract the value. So if you have a 7-point scale and you do the max is 7 plus 1 is 8, so you just do 8 minus your number. Now something that was a value of 7, that was your highest number, 8 minus 7, it drops down to 1. Something that was 1, 8 minus 1, it now becomes 7. So that's how that reverse scoring works. And so whenever you see reflect and then do something, it's essentially just saying to reverse score the item and then apply these transformations. So for a moderate skew positive, it'll be a square root. For negative moderate skew, you reflect the variable and take the square root of that. If the skew is a little bit stronger, you might try a natural log transformation. If it's negative, then you reflect it and then take the natural log, or you can use this exponentiation, which is the opposite of a natural log. And if it's a pretty extreme skew, then you just want to take the inverse of it, so just 1 over that variable. Or if it's negative, then reflecting it and doing 1 over the reflected variable. And here's just a quick demonstration of how if you take exponentiate 5 and then take the log of that, it just kind of cancels that value out. And just quick notes for reminders: for the square root of something, x has to be greater than or equal to 0. If you're trying to take the log of something, x has to be greater than 0. And for inverses, x cannot equal 0. So you have to be mindful of that, because if you're trying to take the log of a variable that has negative values, you'll have to add some sort of constant to it to bring whatever minimum value is, say, up to 1. So if it's a -5 to +5 scale, then you can't take the log of that, and instead you'd have to add that variable plus 6 to make it to make 1 your lowest value up to whatever that highest value is. Same thing for the inverse. You have to make sure that none of your values equal 0, etc. So you may have to adjust some of those with constants. But in this case, just looking at SE and Dep 1, I wanted to re-look at those descriptives just to point out that, like, if ever you don't remember which one is negative and which is positive based on the direction of the tails, mathematically, like, SE1 has a negative skew. You can see that in the descriptives, and for Dep 1 we have that positive skew. Its skew is 1.22. So in this case, if we just look at Dep 1, in this next line of code, all I'm doing is I'm taking Dep 1 and using mutate to change Dep 1 into its inverse. So 1 divided by Dep 1 is what Dep 1 becomes. And then when replotting it, so if this is what that variable looks like untransformed, this is what the variable looks like transformed. And I recognize that you may look at this and be like, well, that doesn't really look like the normal distribution that I'm familiar with. But at the end of the video, I have some additional information where we look at this mathematically. This does have less skew. It does approximate normality, and it's also important to remember that as sample size increase, even non-normal distributions approximate normal distributions at a certain point. For SE1, if we recall, if we look at just that, and we see that it had that negative skew, and so in this case, you might try the reflecting the variable and taking the log, or, like I said earlier, using that exponentiate function. So by exponentiating this, we can approximate something that looks more normal. In this case, I've just selected the 2 because I know which variables already. Again, at the end of the video, I will show what each of these different transformations look like. But for now, I'm trying to keep it more to just the information that you'll need to know specifically for your homework. And so to transform those videos, or to transform those variables, rather, we're going to use that mutate function. And here I have a note that it's bad form in the data world to write over existing data. And instead, whenever you transform variables, whenever you create variables, you want to create them as new variables. So here, instead of just writing over Dep 1 with the transformed with this inverse form of Dep 1, I want to create a variable using the mutate function called Dep1 _ INV, so that I know that, oh, this is the inverse of Dep 1. and then SE1 underscore EXP, so that I know that this is the exponentiated form of SE1. So if I just run that portion of the code, you can see that DEP1 and SE1 have now been created, but we're back up to 7 variables in the data set. So what I want to do is go ahead and pipe that into select down and select not DEP1 and not SE1, so that when I run all those together, I'm back down to just 5 variables as we want. And I've replaced essentially in the data DEP1 and SE1 with the inverse of DEP1 and the exponentiated version of SE1. Whenever you run these mutate functions, if you're trying to create variables that you want to save in the data, it's important that you remember to assign that data frame back to itself. And in other words, when I just run this portion of the code, here it looks like I have created what I wanted, that I have these 2 transformed variables and I have 5 variables in the data set. But if I look just at DF, we can see that I didn't actually write that data into the data frame until I run it and assign it to that data frame by running it all together. And now by doing that, when I look at the data frame, I can see that I do in fact have those transformed variables in the data set. When we look at bivariate scatter plots, one kind of simple, straightforward way of doing it is with the pairs function. And all I'm going to do is pipe our data frame into the pairs function, and I tell it panel equals panel smooth. And this panel.smooth is what actually adds our lowest lines to our plot. So if we just go ahead and run this chunk of code, what we'll see over here is that we get what kind of looks like it functions the same as a correlation matrix, that like our diagonals are reflected of each other, but it just depends on if I'm looking at this column, we have sex on the x-axis as we look down the columns, and this column birth region is on the x-axis as we look down the columns. On this column SRA is what's on the x-axis, but if we look at it across the rows, then here SRA is on the y-axis, here SRA is on the y-axis. And so these as a reminder, these lowest lines, what we're doing is if you just imagine taking a regression line or a line of best fit on a correlation plot, but this is a localized thing. So conceptually, what you could imagine is if we took, say, where SRA is 0 through 10, and then fit a line of best fit, a regression line, and drew that little piece of the line. And then we looked at between 10 and 20 and found the line of best fit and drew a regression line, and then between 20 and 30 and drew the regression line. So that's why our line of best fit, how it can have these like not quite straight lines, is because the best fit of between 2 variables depends on what area of the scale you're looking at of a variable. So when you're looking at these, you want to see that they're more or less linear in some form or fashion, which when we look across these, like in general they are. There are some bends and things, but it's nothing like, major curved lines. We don't have any parabolas where say like SRA at is super high at low levels of depression. It drops down low at the mid levels of depression and then gets high again at the high. So when we say that we're looking for linearity, like we're not saying that we need perfect lines. We're just saying we don't need anything that looks like a question mark, in our data here. So moving along to our variance covariance matrix, this is a really simple thing to do. All we need to do is pipe our data frame into this var function. Var is the variance covariance matrix. Now I have this use equals pair in here, and what this does is, as I mentioned earlier, missing data is kind of the bane of any data scientist's data analyst existence. It's always a pain to deal with missing data, and a lot of functions don't handle missing data by default in any specific way. If there's any NA values in the data, it just changes everything to NA, and it doesn't know what to do with it. You have to tell it what to do with your missing data. And so in this case, this is one of those functions where in order to tell R what to do with the missing data, we're telling it here to use the pairwise complete observations. So whenever it's looking for the variance between, say, SRA and DEP, it's only going to include the all the observations of our 2400 observations that have both of those variables. So if somebody is missing SE, for instance, it'll still include them when it's looking at the covariance between SRA and DEP, but it will exclude that participant when it's looking at SRA's covariance with SE or DEP's covariance with SE, etc. There are other options like case-wise deletion, which means if it's missing any of these variables, then leave it out. So if they're missing SE, like don't put them in, don't get their covariance between SRA and DEP. And so here I've used those pairwise complete observations. And so there may be varying numbers of observations that go into each covariance, but then we're including as much of the data as we can because we're only excluding those specific NA values from their respective covariances. So if we just run here the DF piped into var, we see that we get our variance covariance matrix. And oftentimes, whenever we're doing analyses, we don't actually even need things to be exported. We're working just here in the console. Like we need to look into these matrices and see, are there any anything concerning? What is the information I need out of this to go do whatever the next thing I need to do is. But in this case, we want to go ahead and export this matrix into a CSV so we can open it up in Excel, make it pretty, copy it over into our manuscript, what have you. So this is one of those places where there's a few extra steps involved to make that happen specifically, because when you look at this on the screen, like it kind of looks like there are 6 columns of information here, but in reality, if we just look at the structure of this particular portion that we've run so far, we can see that it's not actually a data frame. It's some lists essentially. So we need to first convert this output to a tibble, convert it to a data frame, and we'll do that by piping that this variance covariance matrix into the as tibble. So say like, hey, like force this thing to be a tibble. I've included this row names equals NA option because one of the things about tibbles is that it doesn't use row names. So what looks like a column over here, it's actually, these are row names. Tibbles don't use row names for good reason. Row names are kind of a bad idea because then that's not information that's actually in the data set. It's information about the data set. And so if you leave off row names equals NA, when you make this a tibble, it's going to remove that information and it won't have those row names. But by putting in row names equals NA, you force it to keep row names. And then when you pipe that into row names to column, it takes those row names and makes them an actual column in the data set. So just by running these first 3 lines here, it gives us our tibble, but you see it's still a 5 by 5. But again, you can see where are those actual, the labels over here on the left-hand side are missing. But when we pipe those into row names to column, it now takes those row names that we kept and puts them as a column of the data set. So now we actually have a 6 columns as a data set. We can then pipe that straight into write underscore CSV and tell it whatever the CSV file name that we want to name it, in this case vcove.csv. And if I were to run this, it will create a CSV file in my working directory called vcove.csv. If I wanted to write it to my desktop or to some other specific file, I would just put whatever my file path to whatever that file, wherever I do want to write it, put it in there. But again, since I'm working straight out of my working directory, I could run this chunk of code and it will take this table right here, make it all into a 5x6 table in a CSV file and write it to my working directory. Now you notice here, I comment out that write CSV. At the beginning, I talked about not having things in your script that write over people's data and such, or that write stuff to other people's computers. And this is one of those cases. So, in your own code, you'll run it like this, but then make sure that you put a comment to comment out the actual writing function. That way, if you send your script to me, you send your script to Anna, that it's not going to, overwrite files on our computer because you had a function that writes something that we ran by accident or whatever. So for the correlation matrix, we're essentially doing the same thing. The only difference is instead of var, the function is core. Again, we have to tell it what to do with the missing data, and we're going to do the same thing. We're going to tell it pair for using the pairwise completions. So again, if they're missing SRA, it will just leave that participant out when it looks at the correlation between SRA and DEP, but it'll leave that participant in when they're looking at the correlation between DEP and SE. And once again here, if you don't need the correlation table, like in a Word document, in a manuscript, etc., like oftentimes when we're doing analyses, we're really just working in the console. So that's all we'd need to run is df piped into core, and we look at our correlations and try to figure out what are those things, what are kind of those thresholds here, where we're looking for multicollinearity, like what is the threshold for multicollinearity? At what point, do things become concerning, and what do we need to do with it there? We look at our correlations in our console, and we make those decisions, and we move about our day. In this case, though, because we specifically want to be able to export these correlation matrices as CSVs, again, we'll just take that correlation matrix, pipe it into as tibble until it row names equals NA, so that we can retain that data from the row names, and then pipe that into row names to column to pull those row names into a column. And then now we'll be able to take that table and write it to a CSV by deleting this, running that full chunk, and it will write this tibble to a CSV called core.csv that gets saved into my working directory. And after you run that and have your CSV in whatever your working directory or whatever your file path is, just come back in, add in that pound sign to comment out to block out the writing there. Finally, or not finally, but for number 8, calculating the determinant. Anna mentioned in class that we did the one assignment where we did matrix math by hand and had to calculate the determinant of things, and she mentioned that when it comes to R, it's very simple, and it's just one function, and this is what that one function is. All we need is if we take our variance covariance matrix that we we made the same way in problem 6, and we pipe that into a function det. That is the determinant function. So by running this chunk, we can see the determinant of our matrix down here. Finally, for the last little bit, how do we dichotomize some continuous variable? There may be times that we need to break something into, high versus low. How you want to do that, will depend on what your purposes are for doing that. But in this case, we just want to say that we'll do a mean split of our SRA variable. And we just want to see if somebody is above or below the mean of SRA. And so we'll use our mutate function to create a new variable called SRA high. And so with this annotation, because I'm using 0 and 1, you know that somebody who has a value of 1 means true. They are the high value of this dichotomous variable. And somebody who is 0 is false, which means that they have a low, they are on the low side of the dichotomy. So we'll do this using the if-else function, which functions by giving it some logical test, and then the output if that logical test is true, and then followed by the output if that logical test is false. So in this case, our logical test is if SRA is greater than or equal to the mean of SRA. And here we have this additional argument, na.rm equals t, which is na remove equals true. Once again, this is one of those things that mean is one of those functions that if you don't tell it what to do with na values, as soon as it detects any na value, then everything becomes na. So if you just run mean of SRA, it will return na for everything. But by telling it na.rm equals true, that says, hey, ignore the na values. And for everything else, where SRA is greater than or equal to the mean of SRA, if that is true, give it a value of 1. Give this SRA high a value of 1. If that is false, give it a value of 0. And so if we run that without storing, without assigning that, so I'm just running this highlighted portion, you can see here where things that were less than the mean are given a value of 0. Things that are greater than the mean are given a value of 1. And again, because we told it na.rm equals true, then things that are na are just left as na and ignored. But if we run this chunk along with that assignment into to overwrite the data frame, now when we look at our data frame, we can see that we have that 6th variable with that dichotomous SRA variable. So that concludes everything that's strictly necessary to know for what will be your upcoming homework assignment. But I wanted to point out a couple of additional things, or a couple of additional ways of doing things that are equally easy. Some people really prefer just to know one way of doing things and get kind of confused by additional information. Others, prefer multiple approaches. But when we look up at problem 2, so for checking those missing values, we used map DFC to see which things are NA, and then used call means or call sums to solve all that. But something else that I wanted to point out is another way of doing that is to use mutate, like we've used for creating or changing variables before, in conjunction with a function called across, which tells us to apply some function across these variables that we're mutating. And in this case, we'd want to mutate everything and apply the function is.na. And this works basically the same way. So when we pipe df into mutate across everything, and the function that we want to apply is is.na, it'll do the same thing. Like this will give us our tibble that has all the trues and falses, and then we can pipe that into call sums or call means. But this everything helper function doesn't necessarily always work. In this case, it does, because we only have the variables of interest. But in some cases, we may need to specify. So it may be this is the exact same thing as this, except for instead of annotating it as everything, we tell it, we use this colon annotation to tell it that mutate across the variables sexf through SRA. And then so take this set of variables, comma, apply this function to it. And so when we do that, in this case, you'll see that it actually that it runs the same thing. These are the same way of annotating, but this, for instance, wouldn't work if we had that full 50 variable data set and we said everything. It's going to run it across everything. Finally, just as a reminder, when you use this colon notation, that only talks about the variables that are between those two variables. So there may be times that when you have those 50 variables, that the way you need to annotate it is by selecting the specific variables, in which case you would need to concatenate those specific variables using this putting them in this C parentheses. That's your combine function. And so when we do that, then again, we will, that's because I took out the dep1 from the data frame. But point is that, be mindful that using this notation may not work every time. Similarly, the colon notation isn't going to work every time. And so if you need to pick and choose specific variables, you'll have to use this combine or concatenate function. On problem number 4 for the skew, I just wanted to run across real quick to show you. So if we go back to our dep1 and look at what that, I guess we'll have to read in our data because we deleted dep1. So I'm just going to come back and rerun that. Then we'll drop back down here. And when we look at dep1, we can see that it has that positive skew. So if we take the square root of dep1, it looks like this. If we take the log of dep1, it looks like this. And when we take the inverse of dep1, it looks like this. And so, I realize that none of those particularly look normal, like I mentioned earlier. But if we take those and we create different variables, so we create the square root, the log, and inverted or inverse forms of those variables, just using mutate, select those and pipe those specific things into our describe function and look at what that skew does, we can actually see that, in fact, that final inverse thing does actually have the least amount of skew, mathematically speaking, even if it doesn't look particularly normal. For the negatively skewed SE1, if we look at that reflected square root, it looks like this. If we look at the reflected natural log, it looks like this. If we look at the reflected inverse, it looks like this. And then once again, if we look at that exponentiated version, it looks like this. So doing the same thing, if I just take that and look at, create all of those versions of the variables and then pipe those versions of the variables into describe to see where things fall. Again, that exponentiated version actually mathematically is the least skewed variable. And then the last thing that I want to point out real quick is for problem number 9, where we said, hey, dichotomize some variables. Sometimes we don't just need to dichotomize it into, high versus low or whatever, but we may need to do it, say, high, mid, and low. Anytime, but if-else functions only work with they only have two outputs. If this is true, then X. If it's false, then Y. But in this case, what if we want to say, well, if SRA is if like less than the mean minus a standard deviation, label it as low. If SRA is greater than the mean plus a standard deviation, label it as high, and label everything else there in the middle as true. Then we can't do that with if else, but we can do that with a function called case when. And case when functions, similarly to if else, but here we're putting in our logical test if SRA is less than the mean minus the standard deviation of SRA. And then we use the tilde to tell this function, if this is true, assign it the value of low. If this logical test is true, then assign it the value, again, that tilde, of high. And then here we just have true tilde mid. And what this true tells it is it's the catch-all that says, like, anything else, anything that doesn't get flagged as one of those two things, mark it as mid. Now, one thing that's missing here that I wanted to point out, because again, it's the kind of thing where if we take this, you got to be careful, because it being a catch-all means that you might miss things. For instance, when we run just this chunk of code, we see that we created a variable called SRA try that's labeled as low, mid, and high. But you might notice here, like all of these NA values were labeled as mid, and that's just because we didn't give it a specific thing to do with those NAs. And then we added in this true tilde mid. So anything that isn't labeled as low or high based on these logical tests gets labeled as mid, even if they're NAs. So instead, what we're missing here is that if SRA is NA, so if that logical test is true, then we want to give it the value of NA. And now whenever we run that, that should actually be a character of NA. And now when we run that, they're at least labeled as NA. And then, like, if we look at that, we can actually run that into a table and see that we have those 248 NA values. One thing just to mention real fast is that this is not actually, notice how these NAs are in red and these are not, and that's because in this SRA try variable, this is not an NA in the sense of R recognizes it as a missing variable, an NA, but rather this is just a label, a character label called NA. So if you were wanting to make this into an actual NA, then you would pipe this into an additional step of mutating, where you could then tell it, where you take that SRA try and you say if else SRA try is in a SRA try. Nope, sorry. That's actually if SRA try equals NA, then return the value of NA, otherwise return the value of SRA try. And now when we run this chunk, you'll see that it converts those characters of NAs to actual missing values. And so that's just one of those things that you need to be on the lookout for. But anyway, that makes this video plenty long enough for this week. Hopefully all of that makes sense. I know that I kind of pushed through it quickly. There was a lot of information that I needed to get through this week in particular. Again, if you have any questions, feel free to reach out. We can set up, either answer questions by email, or we can set up Zoom calls or whatever we need to as needed. And until next time, have a good one.